In this video, we're going to be talking about how to use chain rule to find the derivative or the derivatives of multivariable functions. And we're going to be doing two problems. This is the first one. It's going to be a case type 1 multivariable function. Then we're going to do a case type 2 multivariable function. But case type 1 just means one dependent variable in terms of one independent variable. And let's talk about what that means. So we have this function here, w, which is in terms of the variables x, y, and z. Then we have x, y, and z defined in terms of this parameter variable here, t. So whenever you have a multivariable function like this one and you need to use chain rule to find the derivative, I highly recommend quickly drawing a tree diagram to help make sure you've got everything straight. So we're going to start with the dependent variable w, and we're going to put w at the top of our tree diagram. We know that w is in terms of x, y, and z. So we'll go ahead and say that w here is in terms of three variables, x, y, and z. So if we were taking the derivative of w, we would have to take partial derivatives with respect to x, y, and z. We'd end up with three partial derivatives. But in this case, we've been told that x, y, and z are all defined in terms of t, right? We have an equation for x in terms of t, an equation for y in terms of t, and an equation for z in terms of t. So what we have to do is add to our tree diagram and say that x is in terms of t, y is in terms of t, and z is in terms of t. So now you can label the parts of your tree diagram. The variable at the top is the dependent variable, so we can label that. The variables in the middle are the intermediate variables, and the variable or variables at the bottom are going to be independent variables. And what you want to do is identify how many independent variables you have. If you have one independent variable, then it's a case type 1 multivariable function. If you have two or more independent variables, then you're looking at a case type 2. So as you can see here, we only have one independent variable, it's t. So this is a case type 1 multivariable function. What we're going to be looking to do is find the derivative of the dependent variable with respect to the independent variable. If you just have one independent variable, then obviously you can take the derivative of w with respect to t, and so we can just say the derivative of w with respect to t, and this is going to be the derivative we're trying to find. If you have multiple independent variables, then you'll have to take partial derivatives. So for example, if you had s and t for independent variables, the derivatives you would need to find would be the partial derivative of w with respect to s and the partial derivative of w with respect to t. But because we only have one independent variable, instead of saying partial derivative, we can just say the derivative of w with respect to the single independent variable t. So this is going to be the value we're trying to find, and the formula we're going to use to find this is going to look like this. We're going to take the partial derivative of w with respect to the first intermediate variable. So we're going to say the partial derivative of w with respect to x here. But then we have to multiply that by the derivative of x with respect to t. Because the equation for x is just in terms of one variable, taking the derivative of x with respect to t is, you could say, a normal derivative as opposed to a partial derivative. So we just multiply this by dx dt, the derivative of x with respect to t. Of course, the derivative of w with respect to x has to be a partial derivative because w is in terms of three variables, x, y, and z. Our equation for w is in terms of x, y, and z, so if we want to take the derivative of w with respect to x, it has to be a partial derivative. So this term right here, this product, partial w partial x times dx dt, that takes care of this branch of our tree diagram right here. But now we need to take care of the second branch, and we're going to add the second branch to it. So we're going to say the partial derivative of w with respect to y multiplied by dy over dt, and that'll take care of this second branch here. And then we add to that the partial derivative of w with respect to z multiplied by dz dt, which takes care of our third branch, partial derivative of w with respect to z multiplied by dz dt. So this will be the formula we're going to use. Now we just need to find each of these components. So we're going to say dw dt is going to be equal to the partial derivative of w with respect to x. So if we look at this equation here for w, we want to take the partial derivative with respect to x. Well, we treat e to the y over z as a constant coefficient on this x term here. This e to the y over z is a coefficient. So the partial derivative of w with respect to x is just e to the y over z. then we're multiplying that by dx over dt. So we want the derivative of x with respect to t. Well, that's just going to be 2t when we take the derivative of t squared using power rule. So we're multiplying this by 2t. Then we're going to add to that the partial derivative of w with respect to y. Keep in mind here that we could rewrite this as w equals x e to the 1 over z times y, right? 1 over z times y is the same as y over z. So when we take the partial derivative of w with respect to y, this 1 over z is like a coefficient on the y variable in the exponent. So we just bring that down in front, multiply it by the x. X times 1 over z is x over z, so we get x over z times e to the 1 over z times y, or just to the y over z. Then we're going to multiply that by dy over dt. Again, the derivative of y with respect to t. Well, the derivative of 1 is 0. The derivative of negative t is just negative 1, so we multiply this by negative 1. Then we're adding to that the partial derivative of w with respect to z, so we come back over here, and we could rewrite this as w is equal to x e to the y times z to the negative 1, because we have z in the denominator of this exponent here. It's z to the first power. We can move it to the numerator of the exponent by making the exponent negative instead of positive. So we have y times z to the negative 1. When we want to take the partial derivative with respect to z, we're going to need to use chain rule on this. So we're going to take the derivative of the outside function, which is this exponential function, and we're going to leave the inside function, the exponent, completely alone. Well, the derivative of the outside function, e, is just itself. So what we're going to get is x e to the y z to the negative 1. But then we have to multiply by the derivative of the inside function. So we have to multiply by the derivative of yz to the negative 1 with respect to z. So when we take the derivative of yz to the negative 1 with respect to z, we're going to bring the exponent down in front, negative 1. So we're going to get negative yz, and then subtract 1 from the exponent. Negative 1 minus 1 is negative 2. That's the partial derivative of w with respect to z, but now we have to multiply by dz dt. So if we come up here to our equation for z, the derivative of this with respect to t is just 2, so we have to multiply by 2. So this is our derivative. We just need to simplify it as much as we can. So we're going to say dw dt is going to be equal to, we'll bring this 2t out in front, so we'll say 2t e to the y over z. We'll bring this negative 1 out in front, so we'll say minus x over z e to the y over z. And then here we'll bring this negative out in front as well as the 2, so we'll say minus 2. Then we've got x and y in our numerator, so x and y. But then we have z to the negative 2, so we can move that to the denominator and make the exponent positive. So we're going to say divided by z squared, and then of course multiplied by this e to the yz to the negative 1, which is the same as y over z. Now we could leave our derivative like this, but notice that each of these terms contains an e to the y over z. So let's go ahead and factor that out and say that the derivative dw dt is going to be equal to, we'll factor out e to the y over z, and we'll multiply that by, for the first term, 2t. For the second term, minus x over z, so minus x over z. And for the last term, minus 2xy all over z squared. And this is the derivative of the function w with respect to the independent variable t. And notice how we were able to take the derivative with respect to the independent variable, even though w was not defined in terms of t, it was defined in terms of x, y, and z. We were able to do it because x, y, and z were all defined in terms of t. So that was a case type 1 multivariable function that we took the derivative of using chain rule. Now let's look at a case type 2 multivariable function. In this problem, we've got a case type 2, and let's talk about why we know that. We've got this function z defined in terms of the variables r and theta. So if we start making a tree diagram, we can say that z is defined in terms of r and theta. But then if we go look at our equations for r and theta, we can see r is defined in terms of s and t. So r is defined in terms of s and t, and theta is defined in terms of s and t. So theta is defined in terms of s and t. So here's our tree diagram. Again, we can say that we have the dependent variable z, we have the intermediate variables r and theta, and then we have the independent variables s and t. So because we have more than one independent variable, this is a case type 2 multivariable function. And to find the derivative of z with respect to the independent variables, we're going to have to say the partial derivative of z with respect to s and the partial derivative of z with respect to t. Again, when you just have one independent variable, you can just find the normal derivative of the dependent variable with respect to the independent variable. But when you have multiple independent variables, your final answer is going to be a partial derivative of the dependent variable with respect to each of the independent variables. We've got two independent variables, so our final answer is going to include two different partial derivatives, one with respect to s and one with respect to t. So let's talk about how to find the partial derivative with respect to s first. We're going to say the partial derivative of z with respect to s. So the partial derivative of z with respect to the independent variable s. First, the partial derivative of z with respect to r here. So the partial derivative of z with respect to r. Then we have to multiply that by the partial derivative of r with respect to s. We're taking partial derivatives each time because z is in terms of two variables, so we have to take a partial derivative. And now r is in terms of two variables, so we have to take a partial derivative. So we're going to multiply this by the partial derivative of r with respect to s. But then we have to add to that here the partial derivative of z with respect to theta. So we're going to say the partial derivative of z with respect to theta, and then multiply that by the partial derivative of theta with respect to s. So the partial derivative of theta with respect to s. And notice here how we've used this color orange to get from z, the dependent variable, down to the independent variable s. We had to get to it in both of these locations. We've got an s here and an s here. We had to account for both of those, which we did by going through r and by going through theta. So this is going to be the formula we'll use to find the partial derivative of z with respect to s. Let's go ahead and find that, and then we'll do the same thing to find the partial derivative of z with respect to t. So here we're going to say the partial derivative of z with respect to r. So we find our equation for z. We want to find the partial derivative with respect to r. Well, cosine theta is just going to act like a constant coefficient in front of the e to the r. The derivative of e to the r is just e to the r. So this is going to stay the same. We're going to get e to the r cosine of theta. Then we have to multiply that by the partial derivative of r with respect to s. So if we come over here to r, we want to take the partial derivative with respect to s. Well, t is just going to be a constant coefficient, and the derivative of s is going to be 1. So we're going to get t times 1, or just t. So we're going to multiply this by t. Then we have to add to our result the partial derivative of z with respect to theta. So we come back over here to z. E to the r is going to be like a constant coefficient, and the derivative of cosine of theta is negative sine theta. So the derivative of z with respect to theta is going to be negative e to the r sine theta, and we'll put parentheses around that because of the negative sign. Then we have to multiply that result by the partial derivative of theta with respect to s. So if we look at our equation here for theta, and we want to take the partial derivative of this with respect to s, we're going to need to use chain rule. So first of all, let's rewrite this equation as quantity s squared plus t squared to the 1/2 power instead of the square root. Now we can use chain rule to take the derivative, so we'll bring this 1/2 out in front here, so we'll get 1/2. We'll leave the inside function alone, so s squared plus t squared. Subtract 1 from the exponent, get negative 1/2. Now we have to multiply by the derivative of the inside function with respect to s. So the derivative of s squared plus t squared with respect to s is just going to be 2s plus 0. So we have to multiply by 2s. Now we just need to simplify this, so we'll go ahead and say t e to the r cosine of theta. Here in our second term, we're going to get a 2 in the denominator to cancel with the 2 in the numerator. We'll bring the s out in front, so we'll say minus s e to the r sine of theta. Here we have s squared plus t squared raised to the negative 1/2. If we move this whole term to the denominator, this exponent will become positive, so we'll have s squared plus t squared to the positive 1/2, which we can rewrite as the square root of s squared plus t squared. So that'll be our partial derivative of z with respect to s, but now we need to find the partial derivative of z with respect to t. So first let's build our formula. How are we going to get from z to t when t is in two locations down here? Well, first of all, we're going to go through r. So we're going to say the partial derivative of z with respect to r for that leg. So the partial derivative of z with respect to r. But then we have to multiply that by the partial derivative of r with respect to t. So we're going to say the partial derivative of r with respect to t. Then we're going to add to that the partial derivative of z with respect to theta. So partial derivative of z with respect to theta multiplied by the partial derivative of theta with respect to t. So the partial derivative of theta with respect to t, and that'll be our formula to get from z to t. So now we just need to plug in the values for each of these partial derivatives. We already know from finding the partial derivative of z with respect to s that the partial derivative of z with respect to r is e to the r cosine theta. So we're going to get e to the r cosine theta multiplied by the partial derivative of r with respect to t, which we haven't found yet. So if we come back here to our equation for r, the partial derivative of r with respect to t is just going to be s, so we have to multiply this by s. Then we have to add to that. We've already found the partial derivative of z with respect to theta. We know that it's this negative e to the r sine theta value that we found up here. Then we have to multiply by the partial derivative of theta with respect to t. Well, it'll be the same thing here. We'll get 1/2 times s squared plus t squared to the negative 1/2. But then we have to multiply by the derivative of the inside function with respect to t. Well, the derivative of s squared plus t squared with respect to t is 0 plus 2t. So we multiply by 2t. And now we just need to simplify. So when we simplify, what we'll get here, we'll bring this s out in front, and we'll say s e to the r cosine theta. Again, we'll get the 2 in the denominator to cancel with the 2 in the numerator. We'll bring the t out in front, so we'll have minus t e to the r sine theta. And then we have s squared plus t squared raised to the negative 1/2. We'll move this term to the denominator to make it a positive 1/2, and then we'll rewrite it as s squared plus t squared, taking the square root of that value, and this is the partial derivative of z with respect to t. So when we give our final answer, we have to say that the partial derivative of z with respect to s is going to be this value here that we found. And we also have to say that the partial derivative of z with respect to t is going to be this value here that we found. So because there's two independent variables, it's a case type 2 multivariable function, and our final answer has to include two partial derivatives, one with respect to each of the independent variables.